Welcome to today's session. In this video, we'll tackle the problem of converting integers to Roman numerals, a classic problem that combines knowledge of Roman numeral rules with algorithmic problem solving. Let's dive in. The problem integer to Roman involves converting a given integer into its corresponding Roman numeral representation. Roman numerals are based on 7 fundamental symbols, each representing a specific value. These symbols are I, which equals 1, V, which equals 5, X, which equals 10, L, which equals 50, C, which equals 100, D, which equals 500, and M, which equals 1000. Typically, Roman numerals are written from the largest value to the smallest, arranged from left to right. However, there are exceptions where a smaller numeral is written before a larger numeral to indicate subtraction. For instance, 4 represents 4, which is calculated as 5 minus 1, and 9 represents 9, calculated as 10 minus 1. Other common examples include XL for 40, XC for 90, and CD for 400. Similarly, CM represents 900, which is calculated as 1000 minus 100. Now, the task is to implement a solution that takes an integer as input and outputs its Roman numeral equivalent. The input will be an integer variable named number, and the output will be a string that represents the Roman numeral version of that integer. For example, if the input is 3, the output should be 3, which is a simple representation using 3 I symbols added together. The explanation for this example is straightforward. The number 3 is represented as 3 in Roman numerals, which is the sum of 3 I symbols. For another example, if the input is 58, the output should be LVII. Here, the Roman numeral representation is broken into 3 components: L, which equals 50, V, which equals 5, and 3, which equals 3. Adding these components together gives us the number 58. For a larger number like 1994, we have a more complex combination of Roman numerals. For the input 1994, the output is mixiv. The breakdown of this representation is as follows: M represents 1000, CM represents 900, XC represents 90, and 4 represents 4. Adding these values together yields 1994. The problem also comes with several constraints. The input integer will always be in the range of 1 to 3999, inclusive. Numbers outside this range are not considered valid inputs for this problem. Additionally, Roman numerals for numbers exceeding 3999 are not covered in this task. Some edge cases to consider include the smallest input, 1, which is represented as I, and the largest input, 3999, which is written as mk6. Numbers that require subtractive notation, such as 4, 9, 40, 90, 400, and 900, must be handled carefully. For instance, 4 is represented as 4 and 900 as CM. On the other hand, numbers that correspond to a single symbol, such as 5, 10, 50, 100, 500, and 1000, have direct Roman numeral equivalents like V, X, L, C, D, and M. It is important to construct Roman numerals by starting with the largest possible symbol and working downward. This ensures that the output adheres to the conventional Roman numeral format while properly accounting for subtractive cases when necessary. To tackle the problem of converting integers to Roman numerals, we first considered a brute force approach. The intuition here is to repeatedly subtract the largest possible Roman numeral value from the given integer while appending its corresponding symbol to the result string. For instance, given the input 58, we start by subtracting 50, which corresponds to L. Then, we subtract 5, corresponding to V, and finally subtract 3 ones, represented as 3. While this method is straightforward, it's inefficient for larger inputs due to repeated checks and lacks scalability. A more efficient solution is an optimized approach using a greedy algorithm. Roman numerals have a fixed structure with specific symbols and their associated values, which makes the problem ideal for a greedy strategy. The essence of this approach is to use a predefined mapping of Roman numeral symbols and their values, sorted in descending order. By iterating through this mapping, we calculate how many times each symbol fits into the integer, append the symbol that many times to the result string, and reduce the integer accordingly. This method is both systematic and efficient. Now, let's evaluate the trade-offs between these approaches. The brute force method involves repetitive checks, making it less maintainable and slower compared to the optimized approach. On the other hand, the greedy algorithm stands out for its simplicity, speed, and scalability, as it processes the predefined mapping in a structured way. In terms of space complexity, both approaches require 1 additional space since we only need storage for the result string and a constant lookup table. For time complexity, the greedy approach operates in n, where n is the number of Roman symbols appended to the result string. This is optimal within the problem's constraints. Ultimately, we chose the optimized greedy algorithm as our strategy. Its simplicity aligns perfectly with the predictable structure of Roman numerals, allowing us to efficiently convert integers by minimizing computational overhead and avoiding unnecessary conditional logic. This makes it the most effective and elegant solution for the problem. In this problem, the task is to convert an integer into its Roman numeral representation. Roman numerals are based on specific symbols, such as I, V, X, L, C, D, and M, which represent values like 1, 5, 10, up to 1000. Additionally, there are subtractive combinations like 4, which represents 4, and 9, which represents 9. These combinations help reduce the number of characters needed. The key rule to remember is that Roman numerals are written in descending order of value, starting with the largest. To solve this, we begin by creating a mapping of Roman symbols to their respective values, organized in descending order. For example, M is mapped to 1000, CM to 900, and so on. This mapping will guide the process of constructing the Roman numeral representation step by step. This ordered mapping is essential because it allows us to process the input integer in descending order of Roman numeral values. With this setup, the next step is to initialize an empty string called result. This string will store the final Roman numeral output. Then, we iterate over the mapping, where each entry consists of a Roman numeral symbol and its associated value. For each pair, we check if the current integer value, number, is greater than or equal to the Roman numeral's value. If it is, we append the symbol to the result string and subtract the value from number. This process continues until the integer is reduced to 0. Once all the symbols have been processed, the result string will contain the complete Roman numeral representation. The algorithm uses a greedy approach, always subtracting the largest possible value, which ensures the solution is both correct and efficient as Roman numerals are naturally designed this way. By including subtractive combinations like 4 and 9 directly in the mapping, the algorithm seamlessly handles these cases without requiring additional logic. This keeps the implementation clean and straightforward. The efficiency of the approach is also notable. Since the algorithm processes each Roman numeral symbol only as many times as it fits into the input number, the overall number of iterations is small. For instance, even for the largest possible input, 3999, the algorithm performs a manageable number of operations. We use an ordered list of tuples for the Roman numeral mapping, which ensures we can iterate in descending order of values, critical for the greedy approach. The result string is constructed by appending symbols, which is efficient because Roman numeral strings are inherently short, with a maximum length of around 15 characters. Let's walk through an example to see the algorithm in action. Suppose the input is 58. We start with result as an empty string and number set to 58. As we iterate through the mapping, we skip symbols like M, CM, D, CD, and C, as their values are greater than 58. When we reach L, which represents 50, we append it to result and subtract 50 from number, leaving number as 8. Moving forward, we skip XL and X because their values are also greater than 8. Upon reaching V, which represents 5, we append it to result and subtract 5 from number, leaving number as 3. Finally, we append 3 i's to result to account for the remaining value of 3. The final Roman numeral is LVII. The algorithm is efficient, with a time complexity of 1, because the mapping size is fixed, and the inner loop performs a limited number of iterations. The space complexity is also 1, as the memory usage remains constant, with the result string being the only significant storage requirement. This solution efficiently converts an integer to its Roman numeral representation by leveraging a greedy algorithm. Here's the step-by-step explanation. 1. Define Roman numeral mappings. The Roman underscore mappings list contains tuples of integer values and their corresponding Roman numeral symbols, arranged in descending order. This ensures we process the largest values first, which aligns with the Roman numeral system. 2. Initialize the result string. A variable Roman underscore result is initialized as an empty string. This will hold the final Roman numeral representation. 3. Iterate through the mappings. The algorithm iterates over each tuple, value, symbol, in the Roman underscore mappings list. This loop ensures that we systematically process the number from the largest to the smallest Roman numeral. 4. Determine the count of symbols. The count variable determines how many times the current symbol can be used. This is calculated using integer division, number // value. For example, if number is 3549 and the current value is 1000, count would be 3, since 3549 / 1000 is equal to 3. 5. Append symbols to the result. If count is greater than 0, the symbol is appended to Roman underscore result count times. For example, if count is 3 and the symbol is m, then mmm is added to Roman underscore result. 6. Reduce the number. After using the current symbol, the number is updated to the remainder, number % equals value. This ensures that the next iteration of the loop processes only the remaining value. 7. Return the result. Once all mappings have been processed, the algorithm returns the final Roman underscore result, which contains the Roman numeral representation of the input integer. This approach is efficient, with a time complexity of 1, because the number of Roman numeral mappings is fixed, regardless of the input size. Additionally, the algorithm handles all valid inputs, 1 to 3999, correctly due to the predefined mappings and the greedy strategy. This is the Java implementation for the LeetCode problem integer to Roman, problem number 12. The logic mirrors the Python solution, using two arrays to store the Roman numeral values and their corresponding symbols. The implementation iterates through these arrays, appending the appropriate Roman symbols to a string builder as long as the current value fits into the input number. Java-specific features include the use of the string builder class for efficient string concatenation and explicit type declarations for variables. This approach ensures the solution is efficient and concise, while maintaining readability. To start converting the integer 1994 to Roman numerals, we first initialize our variables. The input number is set to 1994, and we define Roman underscore mappings as a list of Roman numeral symbol pairs arranged in descending order of their values. This ensures we always process the largest values first. We also initialize an empty string, Roman underscore result, to store the resulting Roman numeral. Next, we iterate through Roman underscore mappings, starting with the pair 1000 m. Dividing 1994 by 1000 gives a quotient of 1, meaning we can append m to Roman underscore result once. After appending, we update the number by taking the remainder of 1994 divided by 1000, which is 994. Moving to the next pair, 900 cm, dividing 994 by 900 results in a quotient of 1, so we append cm to Roman underscore result, making it mcm. The remainder is now 94. For the next two pairs, 500 d and 400 cd, both quotients are 0, so we skip these pairs as they don't contribute to the Roman numeral representation. For the pair 100 c, dividing 94 by 100 gives a quotient of 0, so we skip this pair as well. Next, we process the pair 90 xc. Dividing 94 by 90 gives a quotient of 1, so we append xc to Roman underscore result, updating it to mcmxc. The remainder is now 4. For the remaining pairs, we continue evaluating in descending order. Eventually, we process the pair 4, where dividing 4 by 4 results in a quotient of 1. We append 4 to Roman underscore result, making it mxiv. At this point, the updated number becomes 0, so we stop the iteration. The final output for the input 1994 is the Roman numeral mxiv. Now, let's take the input 58 and convert it to Roman numerals. We start by initializing Roman underscore result as an empty string. As we iterate through Roman underscore mappings, the first 5 pairs, from 1000 m to 90 xc, all result in a quotient of 0 when dividing 58 by their respective values. This means these pairs are skipped since they do not contribute to the Roman numeral. Next, we process the pair 50 l. Dividing 58 by 50 gives a quotient of 1, so we append L to Roman underscore result. The result is now L, and the remainder is updated to 8. For the next pair, 40, XL, dividing 8 by 40 gives a quotient of 0, so we skip this pair as well. Continuing with the conversion of 58, we process the pair, 10x, but find that dividing 8 by 10 yields a quotient of 0, so this pair is skipped. Next, we evaluate the pair, 5v. Dividing 8 by 5 results in a quotient of 1, so we append v to Roman_result, making it LV. The remainder is now 3. For the remaining steps, we process the pair, 1i, repeatedly until the remainder is reduced to 0. In this case, we append I 3 times, which updates Roman_result to LVII. The final Roman numeral for the input 58 is LVII. Finally, let's convert the number 4 into Roman numerals. We initialize the input number as 4 and Roman_result as an empty string. As we iterate through Roman_mappings, we find that all pairs from 1000 m to 5v result in a quotient of 0 when dividing 4 by their respective values. Therefore, these pairs are skipped. When we reach the pair 4, 4, dividing 4 by 4 gives a quotient of 1. We append 4 to Roman_result, making it 4. The remainder is now 0, so we stop the iteration. The final Roman numeral for the input 4 is 4. To summarize the approach, the algorithm uses a greedy strategy to convert integers to Roman numerals. It starts with the largest Roman numeral values and works its way down through the predefined mappings. For each numeral, it calculates how many times the current value fits into the number, appends the corresponding symbol to the result, and updates the number by taking the remainder. This ensures that the conversion is both optimal and efficient, leveraging the hierarchical structure of Roman numerals to produce the correct output in a straightforward manner. In this solution, we use a greedy algorithm to convert an integer to a Roman numeral. To start, we initialize a list called Roman_mappings that contains 13 tuples, each representing a Roman numeral symbol paired with its corresponding integer value. This setup is done once and is a constant time operation, or O1. Next, the algorithm iterates through each of these mappings, performing 3 key operations for every tuple: integer division, string concatenation, and a modulo operation. Integer division, which determines how many times the current Roman numeral fits into the number, is a constant time operation. Similarly, the modulo operation, which updates the remaining value of the number, is also constant time. For string concatenation, we generate the Roman numeral symbol repeated by the computed count. Although this could take time proportional to the count is always at most 3 due to the structure of Roman numerals, making it effectively constant time as well. Since there are only 13 mappings, the total work done is 13 times these constant time operations. This results in an overall time complexity of O1 for the entire loop, as the number of iterations and operations does not depend on the size of the input number. Because the algorithm performs a fixed number of operations and iterations regardless of the input, the overall time complexity remains O1, or constant time. Now, examining the space complexity, the Roman_mappings list takes up constant space since it contains a predefined set of 13 tuples, each with a fixed integer in string. This memory usage does not grow with the input, so it is O1. The resulting Roman numeral string, stored in Roman_result, is another factor to consider. The length of this string depends on the input number, but even in the worst-case scenario, like converting 3999 to mnc6, the length is capped at 15 characters. Since this upper bound is fixed, the space required for the result remains constant, or O1. Additionally, the algorithm uses a few temporary variables, such as value, symbol, count, and number, which occupy a constant amount of memory. Therefore, the space complexity of the solution is also O1. This means both the time and space complexities of the solution are O1, making it highly efficient. To put this into perspective, let's compare it to a naive approach. A brute force method might involve iterating over each digit of the input number, manually constructing the Roman numeral by analyzing the place values, units, tens, hundreds, and thousands. This could lead to multiple nested loops and repeated string concatenation, resulting in a much higher time complexity, potentially O(n), where n represents the value of the input number. In contrast, the greedy algorithm avoids these inefficiencies by always performing the same fixed number of iterations. It directly computes how many symbols to use for each Roman numeral, eliminating unnecessary computations. This efficiency allows the greedy approach to achieve both time and space complexities of O1, which is optimal for this problem. In summary, the provided solution demonstrates optimal efficiency. Its time complexity is O1, because it performs a fixed number of iterations in constant time operations. Similarly, its space complexity is O1, due to the constant amount of memory used for the mappings and the output string. Compared to a naive approach, this algorithm is significantly more efficient, achieving the best possible complexity for converting integers to Roman numerals. This makes the solution not only correct but also highly scalable, as it maintains consistent performance regardless of the input size. When working with Roman numerals, there are several common mistakes to watch out for. First, one of the biggest pitfalls is not handling the subtractive cases correctly. For example, the numeral for 4 is 4, not III, and 9 is 9, not VII. If your solution appends symbols in strictly descending order without considering these cases, it will produce invalid results. This is because Roman numeral rules rely on subtractive notation for certain values, and ignoring this can break the expected structure. Another frequent issue is poor handling of edge cases. For instance, failing to correctly process the smallest valid input, like 1, or the largest valid input, like 3999, can lead to runtime errors or invalid output. Additionally, overcomplicating your logic by relying on nested loops or excessive conditionals can make your solution harder to debug and negatively impact performance. Simplicity and efficiency are key here. Finally, some developers misinterpret Roman numeral rules entirely, assuming all numerals must follow strictly descending order. While that's mostly true, subtractive cases like 4 and 9 are exceptions that must be accounted for, otherwise, your output will be invalid. Another common mistake to avoid is ignoring input validation. If your solution doesn't check for invalid or out-of-bound inputs, like negative numbers, 0, or numbers greater than 3999, it can result in undefined behavior or crashes. Now, let's consider what interviewers look for when they test you on problems like these. A key pattern in Roman numeral problems is the ability to translate abstract rules into a structured algorithm. A good strategy here is to maintain a dictionary or list of numeral-to-value pairs, arranged in descending order, such as CM 1000, CM 900, and so on. This ensures you're following the correct order and handling subtractive cases efficiently. When optimizing your solution, clarity should always come first. Start with a straightforward, brute force approach, and then refine it to improve performance while addressing edge cases. Speaking of edge cases, be ready to explain how your solution handles scenarios like the smallest number, 1, the largest number, 3999, and subtractive cases like 4 or 9. Also, be prepared for variations of the problem. For example, you might be asked to work in reverse, converting Roman numerals back into integers. Lastly, when discussing testing strategies, make sure to highlight key cases, such as single symbol inputs like I or V, subtractive cases, and invalid cases like IA. There are also related problems you might encounter that are worth studying. For instance, LeetCode 13, Roman to integer, is the reverse of the problem we're discussing here. Another is LeetCode 12, integer to Roman, which you're already familiar with. LeetCode 38, count and say, involves similar iterative pattern building techniques, while LeetCode 273, integer to English words, tests your ability to map integers to a completely different representation. Now, let's talk about alternative approaches to solving this problem. The brute force approach is one option. Here, you would iteratively subtract the largest possible Roman numeral value from the integer and append the corresponding Roman numeral symbol to your result string. While this method is simple to implement, it can involve redundant checks, which makes it less efficient. A more refined option is the greedy approach. This involves using a predefined list of numeral value pairs in descending order. For each pair, you append the numeral to the result as many times as possible while subtracting its value from the integer. This method is more efficient and avoids unnecessary redundancy, making it a popular choice. Another potential solution is the recursive approach. In this method, you repeatedly subtract the highest numeral value from the integer while concatenating the corresponding numeral to the result string. The code can be cleaner with recursion, but it's important to be cautious about stack space, as this approach might lead to Stack Overflow for very large inputs. Lastly, you can use a hash map lookup for numeral to value conversions. This approach is particularly useful when you need to handle bidirectional conversions, such as converting integers to Roman numerals and vice versa. However, while this method can be powerful, it may add complexity if not implemented carefully. Each of these approaches has its trade-offs, so the best choice depends on the specific requirements of the problem and the constraints you're working with. Understanding these options will not only help you solve this problem effectively but will also prepare you for similar challenges in the future. Great job! We've walked through the process of converting integers to Roman numerals, discussed the key algorithmic insights, and reviewed the complexity. Keep practicing, and don't hesitate to explore similar problems to strengthen your understanding. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!